sand.
Right.
And so much sand you can swap the pumps. I mean, just endless amounts of sand. What we came up with after a couple of failures is that we kept getting stuck. So the valve goes down, valve comes up, and so much slurry of sand is not going to repeat back to the seat. Therefore, you have a hole in the tube,
Right.
and you wash out.
Right.
And so we started looking at it, I was like, why in our rod-driven valves do we not see this problem? And we run in that same amount of sand, water, oil volumes.
Okay.
Actually worse in the water wells because you have no oil whatsoever.
Right.
100% water and a high sand cut, and we don't see washouts in those tools. And
Okay.
why are we seeing it in this tools? Well, there's some physics behind, or physical pumping that's a little different based on an ESP, obviously higher volumes, higher pressures, which we call the washout, where that tool doesn't see those kind, but we still next to never see them.
Okay.
Maybe one out of every 5,000-6,000 wells, and we've seen like 2 or 3 out of everything around Australia, period. It just doesn't happen.
Okay.
So we start going back to what have we done in our rod-driven valve that's different than this valve.
Okay.
And basically what we came back with is that the way we're operating this flap, when you stick a jointed tubing inside there, this is going right into the next jointed tubing, right? And so we're thinking we got plenty of flow rate to do everything we want to do.
Yeah.
We've never seen this eroded, no problems here. But when you start stacking all the pieces together, you've got that pin that you're running the fluid right against. And so we started noticing too that when we did get a washout, it's always on this side, not this side.
Okay.
So what we've come up with is that with this kind of a flow rate or a flow path, we're causing sands to stack and collect back here during operation. So the first time you shuttle, if you don't have a big differential between the casing and the tubing, so fluid level's still high, well's only been on for a couple of days and you have a shutdown, there's enough crap stuck back here that it gets stuck in a port, and the thing won't go back up, wash out.
Okay.
Then also with this flow path, different than the rod-driven valve, it's not a linear, nice, smooth flow path. This is ugly. When you start flowing through this
Right.
thing and seeing how turbulence you've caused right here.
Right.
So this is what our rod-driven valve has in it. So a rod-driven valve has an open piston like this. So the idea being you run the pump or the valve down the hole, you run the rotor right through the middle of this, you space normal operation, no big deal. This floats on a polish rod, one polish rod above the rotor, 10 feet above the rotor. And then the idea is that this just floats. Pump turns on, this just moves out of the way. Life is great, turns off, this lands here, backs up the hydrostatic pressure and opens the piston. Life is simple, and this works beautifully.
Okay.
So we go, okay, well, we originally started this valve with a ball and seat like a rod pump.
Okay.
It worked great. Problem is hard volumes. Trying to stay in 2 7/8 tubing, so we moved away from the ball and seat to the flapper. Flapper got us the volume we wanted, but then the outlying problem is we caused another issue. So what we came up with was this.
And just to clarify, it was not a massive issue. We
No.
saw 3 of them.
Yeah, we saw 3 failures, but the problem is it's in the fields that we want to play in.
Right.
Right, so we can sit back with this tool like we are and stay very selective to where we run at.
Right after they just got done pumping up 50 million pound frac in West Texas.
Right,
And they're using an ESP to flow back,
Right.
report to Wall Street that they got a big well.
Right.
And it's tearing up ESPs, it's tearing up everything down hole.
Right.
And they stick the pump and they'll throw 4 joints of solids above it and blame the valve because
Hey.
the valve's having problems.
Right.
And so we're just trying to make it kind of the next iteration.
Yeah. Gotcha.
It's not that has a problem, it's just we can do it a little bit better.
Right, exactly. What he said. So our challenge was to take what we already know working in the tools that we have,
Right.
6,000 of them in the ground, and say, how do we apply that to this tool and make it a better tool?
Yeah.
And what we're talking about overall. So what we came up with was this type of a design. So it's basically our same actuator that we had before.
Right.
Put a shaft on it, double-ended it, which we can't do that. I'll explain to you in a minute why we don't do that one that way. But with this, you have obviously a much better flow path.
Gotcha.
With fluid going around solid. And then the other thing we added, instead of the tool being that short and the pin right there, we added what we call a flow tube on top of it. So more clearance, separation between here and the pin. Now when this flows out of here, this flows into a larger chamber inside here than what the 2 7/8 is, and again keeps fluid from being harsh or mess with it at all, keep it all flowing linearly. Then we also at the same time harden these parts to, this is 440C hardened to 50 Rockwell, so we made the part harder. And then the same thing here, we took this technology we came up with for our rod-driven system for heavy sand cut wells, and instead of having a single point of contact that we're trying to land on, we gave it multiple points. And this has been just a huge improvement. This gets a little bit on it and you've got to get it cleaned out.
Right.
Which means you need a good differential casing tubing wash when you shut down, and that gets cleaned. Again, that's like Robert's talking about, a well that's making so much sand and you're not getting a drawdown. When you shut down, you're just flushing, this thing's flushing a slurry.
Right. Okay.
With this on here, all of a sudden that wasn't an issue. Just because you've got a place to push that crap, that sand off and catch one of these seats and land. And so that's been the biggest difference, what we put into the tool now.
So are you still using the flapper designs at all, or does it depend on the application or the condition?
We don't see any, I mean, we could make it if we needed to. We're currently not going to.
But you're transitioning.
We're transitioning to that.
Okay.
Yep.
And then for perspective, so like the PCP valve in Australia,
Uh-huh.
those wells are probably 7 to 9% solids by volume.
Okay.
Like, moving 200 barrels a day of water, they'll get 20 barrels of sand out of that same well. It's pretty much one of the nastiest applications in the world for a tool like ours, and it does just great. Versus some of the ESPs where the most we'll ever see is 2%, but you start making that 3,000 barrels a day, and the volume just gets up there and it
Right.
caves in on you after they've pumped these big old fracs.
Yeah.